Hi there, we're back with chapter 4. This will be video 3, our last video for the chapter, and it's just got 2 more examples. But this time our objects are connected to each other by ropes. So we're going to look at some tensions in the ropes. And these objects, they're connected by ropes. So let's look at example number 4. We have a 10-kilogram box and a 5-kilogram box connected by a massless string. We say that in physics when we don't want you to care about how heavy the rope is. Sometimes the rope is important. In an anchor, for example, the weight of the chain itself is actually as important as the size of the anchor. But we're not talking about anchors, no chains, just a rope connecting 2 boxes hanging over a pulley. So the circle is the pulley, and the lines are our rope coming down, and we've got box 1 and box 2. We're going to let box 1 be the 10-kilogram mass and box 2 the 5-kilogram mass. It is important to know which is which because they go different directions. When you have 2 objects connected by a rope thrown over a pulley, the heavy one will go down and the light one will go up. So box 1 is heavier, it's going to come down. Box 2 is lighter, it goes up. You need to know which way they're moving. The boxes have an acceleration of 3.27 meters per second squared. They both accelerate at the same rate because they're connected with a string. If they accelerated at different rates, what would happen would be that the rope would develop slack places in it. And so they have the same acceleration. The question is, what's the tension in the string? So tension, you may remember, is the name for the force in a rope or a string. We have our same formulas that we've used throughout this chapter. F equals ma, W equals mg. Acceleration is v final minus v initial over delta t. Delta x is equal to v0 times t plus at squared over 2. And delta x over delta t is equal to v final plus v initial over 2. We know that mass 1 is 10 kilograms, mass 2 is 5 kilograms, acceleration is 3.27 meters per second squared, up for 2 and down for 1. And we also know that the tension in the rope is the same for 1 and 2 in absolute value. In box 2, the tension will point one way. In box 1, it will point the opposite direction because the pulley changes direction, but the magnitude is the same. So our horizontal forces are going to add up to 0 because we have no horizontal motion. Our vertical forces, each object gets its own equation. So if and I didn't draw in the free body diagrams. How did I screw that up? I am so sorry. So let's see if we can insert. And we'll have to pin that down so I'll see what's going on. We need to insert some objects. So for box 1, I'm going to put it right there. This will be box 1. And then we will have some shapes. So we'll have the weight coming down. It should be straight down. I know my arrow's not straight down. I apologize. In box 2, we have the tension pulling it up, and it should come straight up. And again, I'm sorry, they're not, the one coming down is not straight by any stretch of the imagination. So the one coming up, we said this was for box 1. This is going to be T sub 1. And if I come down here, this will be W sub 1. Again, this is my free body diagram. So this is the free body diagram for box 1. And now I want to draw the free body diagram for box 2. Let's see, he said box 2 weighs a lot less, so I think I'll draw him small. And we want to insert some vectors so its weight comes down. And that's interesting. Sure, we can make it orange. Why not? And then we want to have the weight, I'm sorry, the tension coming up. That's too orange. How about that? We'll just give it a color. All righty. And so if we come across, what have we got going on? So up here will be too close. That is going to be T2. And down here, this will be W2. I guess I'm so used to doing this on the board, I forgot. I usually draw this for people. So these are our two free body diagrams. Somewhere up here, I guess we should label it. Ooh, we don't want to do that. It'll make my equation roll off the page. All right, I'll get it fixed. I promise I will. Okay, we've got our two free body diagrams. This is for box 1. The orange one is for box 2. So the vertical forces, F total in the y direction for box 1 would be mass 1 times A1 in the y direction equals T1 plus W1. For box 2, it's mass 2 times acceleration in the y direction, which would equal weight 2 plus T2. Okie doke. We want to find the weights. W equals mg, so weight 1 is equal to m1 times g, so 10 kilograms times 9.8 meters per second squared, which gives us 98 newtons. It's pointing down. Weight 2 would be m2 times g, so 5 kilograms times 9.8 meters per second squared, or 49 newtons, also pointing down. The weight always points down. Now, we need to look at our two equations. Here are equations for the object. So if we look at the vertical force equation for box 1, we can use it to find T1. So M1 times A1 equals W1 plus T1. M is 10 kilograms. A is, notice I wrote down negative 3.27 meters per second squared. Why did I do that? Because I said up is positive, and if up is positive and the box is moving down, it's going to have a negative acceleration. So negative 3.27 meters per second equals weight. The weight went down, so that's negative 98 newtons, and T1 we do not know. So 10 times 3.27 is 32.7, but it's negative, so negative 32.7. We have to add 98 to both sides, and when you do that, the math is 65.3 newtons. But T1 and T2 and all the T's are the same because it's a single piece of rope, so the tension in the rope is 65.3 newtons. 65.3 newtons. And we're done. We can move on to the next example. So we have two boxes. They're pulled upward with 24.5 meters per second squared constant acceleration. We want to know the tension in each of the cords. So we have two ropes. Rope 1 connects box 1 to box 2. Rope 2 connects box 2 to whatever is dragging it up. We know M1 is 5 kilograms, M2 is 10 kilograms. We know the accelerations are the same. We're going to make up positive, and we want the two tensions because we have two separate ropes. And by now we know if we're only looking at tensions, we just need W equals mg and F equals ma, and any equations we can write based on the free body diagrams. So we have two objects. We're going to have two free body diagrams. For box 1, T1 goes up, weight 1 comes down. Here is box 1, the 5 kilogram box. Guess I should have made it smaller. I think I will. So our free body diagrams, box 1, T1 comes up, W1 comes down. Let's look at box 2. Box 2 has T2 coming up. That part's easy. But hanging down, it has a rope. So the rope is T1, but it also has its own weight. Every object hanging by a string has the tension of the string pulling up and its own weight coming down. Box 2 has something extra. It has this additional string hanging on it, pulling down on it. All right, so remember our vertical force equations come from the pictures. So F total in the y direction for box 1 is mass 1 times A1 is equal to T1 plus W1. For box 2, it's F total in the y direction for box 2 is equal to mass 2 times acceleration 2 is equal to T1 plus T2 plus W2. Well, it looks like we need the weights to get anywhere with these problems. There's no angles, so we have to find the weights. W equals mg. W1 is equal to M1 times G, so 5 kilograms times 9.8 meters per second squared, or 49 newtons. For box 2, W2 equals M2G, so 10 kilograms times 9.8 meters per second squared, which equals 98 newtons. So we have the two weights. Remember, we need to use these two equations. The box 2 equation is more complicated than the box 1 equation, so probably box 1 is going to work. We know its mass, we know its acceleration, we know its weight, we can find T1. If we have T1, we can use that to find T2. So that's what we'll do. We'll find T1. We're going to find T1, we're going to make up positive, we write the equation down, and we plug in. So M1 is 5 kilograms, A1 is 24.5 meters per second squared. It's going up, so it's a positive acceleration. T2 we do not know. W1 is 49 newtons and it points down, so it's a negative number. See the little minus sign? It's a negative number. So when you do your arithmetic, 5 times 24.5 is 122.5. We've got minus 49 on the right side, so I'll have to add 49. I skipped a step, as you can see. And we end up with 171.5. If you have trouble with the algebra, include the missing step. If you still screw it up and don't get the same answer I did, ask for help. So T1 is 171.5 newtons up when we're talking about box 1. Let's look at the boxes. So T1 points up in this picture. Look what happens over here on box 2. Does it point up? No, it points down, which means when we use this second equation, T1 will get plugged in as a negative number. So here we go. Second equation, M2 times A2 equals T1 plus T2 plus W2. So 10 kilograms times 24.5 meters per second squared equals T1. Yes, it was a positive 171.5 when we found it, but for this equation, because it's a different object, it's pointing down, that makes it negative 171.5 newtons, plus T2 minus 98 newtons, weight 2 points down. So T2 will be, well, 10 times 24.5 is 245. We'd have to add 171.5 to both sides, add 98 to both sides, and we get 514.5 newtons. It is a positive number. We know it points up. And that agrees with our picture. Yay! All right, I'm sure you have study guide problems. This will stop the video.